Greetings, everyone. Today we're going to explore writing and evaluating piecewise functions. You should have a note sheet for this. If you don't, just take notes in your notebook or print it off of Google Classroom. The first thing we need to talk about is what is a piecewise function? The name describes it. We're talking about a function that's made up of pieces of different functions, which are results of their different domains or x values. Meaning, I'm talking about a function maybe from -3 to 0, and then a different function from 0 to 5. So let's apply this idea to the real life. Let's say we're at a job, and we make $8.50 an hour for up to 40 hours. But after 40 hours, I make time and a half. Therefore, at 40 hours, my graph would change its slope. So let's talk about how I would write this mathematically using the correct notation. If I have a linear function that describes that I make $8.50 an hour for up to 40 hours or less, that would represent this function. So I have to state the function first, comma, what my restrictions or limits are. Now we could write it a couple of ways. This is an inequality notation. So we're saying that when x is less than 40, and really we should say greater than or equal to 0 as well. But we also know interval notation from 0 to 40. And then if we talk about the function for my time and a half is $12.75 an hour. There's my function, my linear function. And the restrictions are after my comma space when I'm working greater than 40 hours. Now, I could put more of a limit on this. I could say up to how many hours in a week, right? I can't work more hours than exists in the week. So I could have an upper limit as well. And we know that we could also use interval notation. Now notice the difference here. I used a bracket on the first 40 because it was or equals to, and I used a parenthesis because there was not on the second 40. In order for this to be a function, I can't exist twice at one point. It wouldn't pass the vertical line test. So we're going to work on that. We're going to work on what does it mean if I have the same point. Only one of them can be a solid dot and one an open dot. All right, let's do some evaluating though. Let's say I give you these three functions and they have three limits. I've got less than 4, between 4 and 7, and greater than 7. Linear functions, quadratic, pretty basic. The question is going to state, find f of -2, meaning we're going to plug -2 into one of the functions. The only thing you need to decide is which function, meaning which boundary does -2 fit in? Well, let's see, -2 is less than 4, so I am going to substitute -2 into the first function. I'm replacing the x, and I am solving. Let's take a look at the next one, f of 8. If I'm talking about 8 is greater than 7. So I'm going to use this function. You might be thinking, well, I can't plug in 8. There's no x there. Correct. If there's no x, then the function itself is your solution, because graphically, that would be a horizontal line. So it doesn't matter what my x is, I exist at 3. Let's look at the last one, f of 4. All right, let's take a look. There's 2 4s in my restrictions here, but I'm going to use this one because 4 is greater than or equal to 4. It has to be or equals to if it's the same number, right? So I'm going to plug in 4 into x in my second function. So I'm going to arrive at 16 2/3. Don't make it more complicated. Keep it basic with those fractions. Let's try evaluating when I'm given a graph. It's the same idea. If x is -6, my goal is to find where y exists. If x is -6, where do I exist? I exist right here. I exist at 5. Let's try another one. 1. When x is 1, what does y equal? If you notice, there's 2 dots, but I care about where I exist, which means the closed dot is what matters. The third one, -1. When x is -1, what is my y value? Where do I exist? I exist down here on the curve, which is at -7. Now, occasionally, might you have to make an estimation with a graph? Yes, but we'll try to keep them as integers. All right, now let's do the flip. So that was the evaluating piece. Now we want to take care of the writing piece. So to start off, I'm going to color coordinate. We want to create a function rule for this line. That's all we want to worry about right now. Now, it's a line. So my mind goes to slope-intercept form. Y equals mx plus b. I need to find my slope, and I need to find my y-intercept. And I can count. My y-intercept is 3. My slope is down 1, right 1, down 1, right 1. So my slope is -1. Let's take a look at the green line. I, again, want to, do I want to use slope-intercept form? Let's talk about that. I would have to extend my graph and find my b value. But we spent all that time talking about translated form. So I'm going to actually use translated form, meaning y equals mx minus x minus y. Remember how that looked? That's my shifts. So let's take a look. I'm going to use this open circle as my point. That point is 2, -1. So I'm going to have y equals, I can still count my slope, down 2, right 1, down 2, right 1. My slope is -2. My x point, remember if it's in parentheses, I change the sign, so instead of +2, it's -2. My y value says -1, and remember, the vertical shift on the outside is what it is. It's going to stay -1. Now, on this one, could I have counted and found my b value? Yeah, but that's more work. I'm just going to use a dot that's already on the graph. Therefore, your piecewise functions, when you write them, can look different than your neighbors. That's okay. It depends on which form of a line you choose. All right, let's write this in the formal notation. F of x equals, I have 2 functions, so I show my set with a squiggly bracket. My first function is -x plus 3, comma. Let's state the restriction. X, well, if I take a look, 2 is my magic number, right? I exist when x is less than or equal to 2. See how it's a solid dot here on that red function? And it's going left. It's less than +2, excuse me. Let's take a look at the green function. I'm going to write my function, comma. Well, again, I'm going to use that 2 value, but you'll notice the x values are greater than 2. It's an open circle, so it's just greater than. All right. We could also work with that idea of -infinity to 2 bracket, or we could look at 2 parentheses to infinity. So a couple of things to think about when working with piecewise functions. We're essentially writing a domain for each piece of the graph. We've been working on domain and range, okay? So that's our goal. What's the domain? What's the x limits? Don't forget that equations of vertical and horizontal lines. If I slice the x-axis at a certain number, that's my equation. Like x equals 7 would be a vertical line through 7. Or vice versa, if I say y equals some number, like let's say y equals -3, then I'm slicing the y-axis at -3. So just remember how to write those equations. And then also remember that general form. When I'm talking about a line, let's talk about that translated form. Okay? You don't need to find the b value if you know a point on the line. And it plays out the same way with absolute values. We are going to write some absolute values. We've done that before. You're going to keep seeing that. Remember, horizontal shift of the vertex, vertical shift of the vertex, and then what is my stretch or compression? So let's take a look at this graph. I see 3 pieces. So I'm going to have, first of all, a squiggly bracket for f of x, and I'm going to have 3 functions. I'm going to start with this one with color coordinate. So I've got this red function here, right? I see it has a point at -1, -1. So I'm going to use that in my line. So remember, I'm going to make a little note. M equals x minus x plus y. My slope is down 1, right 2. Down 1, right 2. Rise over run. The x value of my point says -1, so I'm going to add 1. The y value is -1, so it stays -1. Comma, space, let's jump into our limit. My function exists when the x values are less than, whoops, wrote that on the wrong side, when x is less than -1. Less than because it's an open circle. Let's look at the next line. It exists right here. I'm going to use green for this line. That is a horizontal line. A horizontal line is y equals that number. Well, I'm crossing or I'm slicing the y-axis at 2. That is my function, y equals 2. Let's state the limits. I have a compound inequality here. I am greater than or equal to -1 because I have a solid dot here at -1. Now you'll notice this other dot's off a little bit, but look at the dot above it. We want to use that same value. So I'm less than or equal to 3. Or equals to because it's solid. All right, let's take a look at the purple line. I've got a decreasing linear function. And I have this point here, which is at 3, 4. Let's write the equation of a line. I'm going to use translated form. My slope is -1. Down 1, right 1, down 1, right 1. My x is 3, so I'm writing subtract 3. My y value is 4, so plus 4. Comma, space. My graph, my x values, my domain is greater than the x value of 3. I exist when the x value is greater than 3. That's that magic line, that boundary, that limit that I am dealing with. Now, you're going to have to come up with a method. Would it be easier to write all the functions, label the graph with points? You have to decide what order. I like to go just piece by piece. Let's take a look at this one. I have 3 functions I see colored. Now you'll notice that light blue one is an absolute value. But here's the thing, you guys. You could, if done correctly, split that up into 2 linear functions and have 4 functions listed. For practice though, I'm going to use absolute value. So let's look at that blue function. I see I have a stretch of 2. Absolute. The vertex is at -3, 2. So inside, it's x plus 3. And on the outside, it's plus 2. Comma, space. Take a look. Here's where my graph stops. My graph stops at the x value of -2. Now there's no dot there, so here's where we got to play a little bit of a game. I'm definitely less than -2, right? So I'm just going to leave it as less than, and let's jump to the next function and talk about it. The red function is a horizontal line that slices the y-axis at 4. So that's my function, y equals 4. My boundaries for my red function are between 2 and 3. Now, you might be thinking, let's talk about this or equals to. If the light blue function, if you choose less than there, then you choose less than or equal to on the red function. Now here's the thing, you could flip that. You could make this one or equals to and this one just less than. That would also be correct. What can't happen though is I can't have or equals to on two functions because then it's not a function. Okay, I always need, if you think about it this way, I always need a solid dot inside of an open dot if they overlap. So on my 3, I get to decide. I'm less than 3. Do I want to be less than or equal to? I'm going to make these the same. We'll talk about it a little bit further when I address the purple function. Now the purple function has this point of 3, 4. I'm choosing that point. You could use this point. You could find the y-intercept. There's lots of ways. Either way, my slope is down 3, right 1. Down 3, right 1. Parentheses because it's linear. X, I'm using the 0.34, so my x is minus 3. I'm using the 0.34, so plus 4 goes on the outside. This seems silly, but be careful. This is absolute. This is linear. Parenthesis versus bar. All right, my x values, I'm going greater than the x value of 3. Now be careful. If I choose this to be or equals to on the red function, then this one cannot. The purple one has to be just greater than. Okay, so again, you can't have overlapping or equals to points. That's going to take some practice. All right, this is going to be a little bit of a tougher unit, so make sure that you ask questions. Make sure you check out Google Classroom. Consider if you were taking notes during this video to rewatch without taking notes so you're less distracted and trying to keep up. If you have any questions, but I'm unavailable, as always, take a look at the Sabre Center schedule. And until next time, have a good one.